Good evening, Lamai. Let's start the session for today. Today we are going to start with heat and enthalpy, which is appearing at your page number 7 no? Of your tutor, right? Let's discuss about what this heat means and what this special term enthalpy means. First, let's discuss about the heat, what this heat means. So actually, heat is kind of an energy which will be transformed from a system at low temperature, from a system at high temperature to a system at low temperature. So the energy transfers from a higher temperature to lower temperature is referred to as the heat, right? So basically, when it comes to measuring the heat, right, by measuring the temperature difference of the two systems, or the system at the initial state and the system in the final state, by measuring the temperature difference, actually we can come up with the heat transfer, the heat change. So for that, basically we use the equation Q is equal to mc theta, right? So that is the equation we use now. The equation we use to measure the heat change is actually Q is equal to mc theta, right? So actually, even though we memorize this equation as Q is equal to mc theta, the actual equation is Q is equal to mc delta theta or delta T. It will give you the heat change. Right, happened in a process. Q is equal to mc delta theta. And you know about these terms, right? M is the mass, C is the specific heat capacity, and delta theta is the temperature change, right? Okay, this is the equation, right? We use to come up with the heat change, right? When we are thinking of our systems in chemistry, we can measure these heat changes in two types of systems. What are those two types? So basically, in chemistry, we will come across two types of systems. The first kind is systems maintained at constant volume. So those are referred to as constant volume systems. So when we are learning about gaseous state, we had done much of your experiments, much of your things in these kind of systems, right? We came across glass bulbs, rigid vessels. So all those kinds comes under constant volume systems, right? The second type of systems we would observe in these practical situations is actually the constant pressure systems or constant pressure volume vessels, right? Let's discuss about these two systems first, right? As an example, I would consider this kind of system for a constant volume system. So if you think of this kind of a vessel with a piston which is actually fit to the vessel like this by a nail even. So this is referred to as a constant volume system. You could observe any kind of change appearing with this inside the system, right? Yet the volume of system won't change. As this is fixed to the vessel. This is an example for a constant volume system. So if you think of a constant pressure system, this is a good example. Say you have a piston vessel like this, and this is your piston, and say it can move up or down. It is not fixed. So such a thing is referred to as a constant pressure system. So how it works? Basically, this piston will move upwards or downwards until the pressure inside the system will equal to the pressure outside the system. So it's like the pressure in, until the pressure in is equal to the pressure out, basically the atmospheric pressure in this case. Right? Let's say atmospheric pressure. Until this happens, until these two pressures are equal, the piston will move up or down. That is how these kind of systems work. If you are doing a reaction where gas molecules are released, so inside pressure will build up with such a process. Then the inside pressure will be higher than the outside pressure, so that piston will move up. Right? So if you are doing a reaction here where the gas molecules are consumed, so the pressure will drop inside system as P is equal to nRT. When N drops, the pressure will drop, so that P in is less than the P ATM, so that your piston will move down. Right? So such that the system works, the system will respond to pressure changes inside the vessel. Right? Okay, that is how this kind of a constant pressure system works. Right? Let's think of one same chemical reaction, but done in these two types of systems. One same kind of chemical reaction done in these two kind of systems, and after that we'll discuss how the heat changes. After that we'll compare basically how the heat changes will occur with those systems. Right? So what is the example I'm going to take here? So I'll take this example reaction, which is appearing in your note as well, right? So the sink solid, so I'll take it like this. So here, sink solid reacting with H2SO4 to produce the zinc sulfate and H2 gas. Examine this reaction happening in these two types of systems. Here the gas, H2 gas will produce, right? Okay. So if you are to do this reaction inside the constant volume system like this, what will happen? So let's say this is the H2SO4, and you have added some pieces of zinc to this thing. Then the reaction will occur when the zinc particles connect with the H2SO4 molecules. When the zinc particles, right, find the H2SO4 molecules, there the reaction occurs. So let's say these are the points where the zinc particles meet the H2SO4 molecules. There only the reaction would occur. So I may prefer these points as reaction sites. So from these reaction sites, this reaction occurs. And this reaction is referred to as a exothermic reaction. Right? This is a reaction where your acid reacts with a metal. So acids and metals, such reactions are referred to as exothermic reactions. That means those will liberate some heat to the environment. So this thing will produce some heat as well, right? So as this reaction occurs, these reaction sites will generate some heat and release some heat to the solution like this. So from these reaction sites, heat will be generated, as this reaction will generate heat. From all these reaction sites, heat will be generated, so that you would observe kind of heat change, kind of temperature change, the kind of temperature change if you had put a thermometer to your vessel. So we can observe the temperature change with this process. Right? That is clear? So not only the heat, but also some of the gas molecules also will be released, right, by the reaction. Some heat as well as H2 gas molecules will release, right? So H2 will also release. So when the H2 releases, the pressure inside will increase compared to pressure outside. So pressure in will be now greater than the pressure outside. So let's take it as 1 atm, the normal atmospheric pressure. So in this kind of system, this is total scenario. When the reaction occurs, heat will release as well as H2 gas. As H2 gas releases, the pressure inside will increase. So it will be now greater than the P1 1 atm. That will happen. But anyway, as heat is liberated, the temperature of the solution will also increase. Temperature of solution will also increase. So as we kept constant the volume of the system, these processes are referred to as constant volume processes. Constant volume processes, right? So such kind of a measured temperature can be considered as a temperature change in a constant volume process. That is why I put this subscript V, temperature change in a constant volume process, right? With these kind of systems. So basically P in is greater than 1 atm. This is not equal to the P out, right? Okay. So this is about these kind of ones, these systems, how this works with the same chemical reaction, right? So again, with these systems also, the reaction occurs at reaction sites. Reaction will happen at reaction sites, right? So you will produce some heat will be generated from these reaction sites, right? So you will observe some increasement of temperature from your thermometer, and this can be referred to as delta Tp, the temperature change measured in a constant pressure process, right? Why we are saying so, a constant pressure process? The thing is, actually not only the heat but also the H2 gas is also will produce at this process, no? Then what will happen? As H2 gas is producing, right, the pressure inside the vessel will increase. So what will happen? As pressure increases, then the 1 atm here, as pressure increases than the 1 atm here, what will happen? The piston starts to move up. Piston starts to move up to decrease your pressure. Basically, by increasing the volume, when the piston starts to move up, this volume will increase. No? By increasing the volume, basically you can decrease the pressure. That is how you attain again the 1 atm pressure inside the vessel. Right? The idea is clear. So when the H2 gas releases, the pressure inside the vessel will increase. It will increase than the 1 atm, which is the atmospheric pressure. So pressure here is greater than the pressure here. So what will happen? So this will move upwards. When this moves upwards, what happens? As volume increases, the pressure will drop. Pressure will drop when this moves upwards. So when the pressure inside the vessel equals to 1 atm, the movement of the piston stops. So anyway, we can see or we can observe a movement of piston by this process, right? So piston will move up, right? You can say piston will move up, right? That is how the reaction happens in a constant pressure system, right? Okay, right. So let's examine the two, right, heat changes which will occur with these two processes, right? The first thing, what about the temperature change? So basically, all the heat released by this process will be used to increase the temperature of the solution, as no heat is consumed to do any other process in the system. All the heat produced will be used to increase the temperature of the solution. No heat is used to do any other process. Any other process is not happening in the solution. So we can say with the constant volume system, all the heat released by reaction will be used to increase the temperature of the solution. But here this heat is used to increase the temperature of solution. Not only that, but also some of the heat released here will be used to move the piston as well, as movement of piston is happening here. So some of the heat energy released, some of the energy released will be used to move the piston, to provide the kinetic energy to move the piston, right? So the heat used to increase the temperature of the solution is less than compared to this situation. Why? Because some of the heat is used to move the piston as well, right? So we can write, not all the heat released by the reaction is used to increase the temperature of the system. Same as a solution, let's see, solution. Some of the heat released is used to move the piston as well. So you clearly see the heat change occurring here will be less than the heat change associated with this process, right? Why is that? Because temperature change with this process is actually a lower value than the temperature change observed with this value. this system, right? Because only less heat is used to increase temperature here. The other heat is used to move the piston. But here all the heat released is used to increase the temperature of the system. So you will have observe some greater temperature change here, less temperature change here. So that if you are applying that to the Q is equal to MC theta, so we can say the Q measured in a constant volume pressures is equal to MC delta theta or delta T, the same thing, right? In a constant volume process. So as this thing is high, the measured heat in a constant volume process will be high. If you are to do the same process in a constant pressure system, we can say the heat change, you can take it as QP in a constant pressure process is equal to MC delta TP. As this value is low, in this case, this QP, the measured heat change in a constant pressure process is low. So we clearly see, even though the same reaction happens with the same amount of times, same amount of reaction happens with the same amount of time, we observe the same thing, right, with 1 mole each. Even though the same reaction occurred with same amount of time, still you would observe some two kinds of heat changes, as the type of systems are not the same, right? In a constant volume system, you would observe a greater heat change for this reaction, while in a constant pressure situation, you would observe a smaller heat change for the same reaction. So what we have to observe here is the heat change. The heat change may not be the same for two types of systems. If you are doing the process in a constant volume, or if you are doing in the process in a constant pressure, right? For two types of systems, the heat change may differ. So then what is this enthalpy? What is this enthalpy? So the enthalpy means this heat change happened in a constant pressure process. The heat change happened in a constant pressure process, or a constant pressure system is referred to as the enthalpy. That is the specialty with the enthalpy. Enthalpy is not any kind of a heat change, or enthalpy is not any kind of a energy change. It's the heat change happened in a constant pressure process. Heat change happened in a constant pressure process, or a system is referred to as the enthalpy change, right? That is the enthalpy and enthalpy change, right? So we can say, right, enthalpy is what? Enthalpy is the heat change. Enthalpy is the heat, or enthalpy change is the heat change associated with a constant pressure process. Right? That is enthalpy. Got the idea? Alright. See what they are saying with your note. Actually, these things are there in the first page, that means page number 7 of your note. So you can draw these ones. Just draw these two diagrams there. Do these two diagrams. That space is there. Is a constant volume situation, and that is a constant pressure situation. So just draw these two diagrams and complete the note first of all, before we go into the next page. Right. Okay. let's go to the next page now. At the page number 8, you have the definition for the enthalpy, which we have discussed, right? It is said like this change in heat, the change in heat in a constant pressure process is called as the enthalpy change, the delta H. Right now, that is given. So that is all about enthalpy, right? Let's discuss more about enthalpy, right? So the enthalpy is the enthalpy change is the change in heat in a constant pressure process, right? Okay. Right. Let's discuss more about enthalpy. Now, enthalpy is kind of energy, right? It is a heat energy associated with a constant pressure process, right? It's kind of energy, right? It's kind of heat energy associated with a constant pressure process, right? So it's kind of energy, right? So this enthalpy is referred to as a state function. Enthalpy is referred to as a state function, like temperature, pressure, even the volume, number of moles, like that, right? State functions are the parameters which defines the state of your system, right? So enthalpy is another such state function. So enthalpy is a state function which defines your system. So for state functions, this thing is appearing. For a state function, we can take the change of the state function. We can take a change of a state function by considering the final state and the initial state. So by considering the value of the state function at the final state minus considering the value of the state function at the initial state, we can come up with the change of a state function. For that can be applied for enthalpy as well, because it's a state function, right? So when it comes to a chemical reaction, so for a chemical reaction, when considering a chemical reaction, chemical process or chemical reaction, we know the final state is referred to as the product state. The final state is referred to as the product state. So we can write it as the enthalpy of products. And the initial state is referred to as the reactant state. So enthalpy of reactants. So for chemical reaction, we can look at the enthalpy like this. For a chemical reaction, the enthalpy change is the enthalpy of products minus the enthalpy of reactants. Enthalpy of products minus the enthalpy of reactants. That will give you the chemical, the enthalpy change of a chemical process. Right? Right. Okay. So this says the enthalpy change of a reaction is equal to the total enthalpy of products minus the total enthalpy of reactants. Right? That is what this equation says. The enthalpy change of a reaction is equal to total enthalpies of products minus total enthalpies of reactants. So if you need what enthalpy means, so the enthalpy is actually the heat energy associated with the constant pressure situation. The heat energy of the system associated with the constant pressure situation is referred to as the enthalpy, right? The idea is clear. Right? This is all about the enthalpy change, right? Okay. Next one. So let's go to the note there. It says the enthalpy change of reaction delta H is the difference between the total enthalpies of the products and the total enthalpies of the reactants. That is clear now? Right? That is what it says. Right. That is okay. So then they have asked, they have written what enthalpy means. So enthalpy can be defined as heat content of the system at constant pressure situation. That is also clear now? Enthalpy can be defined as the heat content of system at a constant pressure situation. That is clear stuff, right? Okay. So, but the next statement is very special. Yes, the enthalpy is the heat content of a system when it is at a constant pressure. That is the enthalpy, right? But the next point is very important. What is that? It says it is impossible. It is impossible to measure this enthalpy. It is impossible to measure kind of absolute value for this enthalpy. Actually, what we can do is to measure the enthalpy change. What we can do is measuring the enthalpy change, but not the enthalpy. Enthalpy is the heat content of a system at a given pressure. Heat content of a system at a given pressure. That is the enthalpy at the constant pressure, the given pressure. Right? Actually, we can't measure that thing. What we are doing is just measuring the enthalpy change by considering the temperature change happened there. Right? To use the equation Q equals mc delta theta, we need to come up with the temperature change. Right? So that is a change we are going to examine there, not just the absolute value of the enthalpy. So what we are doing is actually we are coming up with this value, right? That means the difference between the initial and the final states, not the exact value of the state, not the exact value of the products, not the exact value of the reactants. We are not coming up with the absolute values of the enthalpy of the reactants as well as products. What we are coming up is actually the difference between the reactants and the products. That is what it says. It is impossible to determine the enthalpy of a substance. Impossible to determine or get the absolute value for a substance. So it is a change in which the change in enthalpy that we actually measure. The things are clear now? Right. It is about enthalpy. Now let's discuss about the factors. Next point is about the factors affecting this enthalpy, right? So these sections are right, which theory parts, right? So let's quickly go to these sections, right? Towards some calculations, right? Okay. So what are the factors affecting this enthalpy? So we'll discuss about 4 factors affecting the enthalpy, right? The first thing is pressure. Factors affecting enthalpy as well as the enthalpy change. Right? Number 1 is the pressure. Pressure. Right? It is very clear, Lamai, the pressure affects the enthalpy. So it's like this now. So what we are doing is this now. We have piston vessel like this. Let's take the early example. Right, you have this thing, and the heat will be released from the reaction sites like this. Right? This whole system we had discussed. Right? So H2 gas will be released as well. This is the thermometer we had used to compute delta T, which will be ultimately used to come up with delta Q as well as right the enthalpy change, right? So this P out and this is P in. So the first point is about pressure. So if you are having a greater pressure, not like 1 atm, let's like just take it as 5 atm kind of thing. If you are with a greater pressure here, right? So you have to put some more energy to move the system with this piston compared to 1 atm here. Just what we are doing is just right moving this piston, right? So if you have greater pressure here, maintain at a greater value the pressure, you need to apply more pressure to move this piston upwards, right? That means to give some more pressure, more of the heat liberated will be used, so that less amount of heat will be used to increase the temperature of the solution. So more of a drop of the enthalpy will observe. Measured heat will observe. So enthalpy will change with greater pressure. Right now? So pressure effects. Right? The constant pressure at which we keep the system. If it is 5 atm, you need to come up with greater force. For that, greater amount of heat liberated will be used like that. So that less amount of heat will be used to increase the temperature of the system. That is what we are measuring actually as Q. Right? So when pressure changes, the measured heat will change. That means enthalpy will change, enthalpy will change. Right? So just write like this, like that thing. Number one, the constant pressure at which the reactants and the products are in. The number one, constant pressure at which the reactants and the products are in. We are maintaining at the constant pressure. Now it is 5 atm, right? I just change the value like that. This sound, this pressure, these effects. The constant pressure at which the reactants and the products are in. Number two, second factor affecting the enthalpy or the enthalpy change. The temperature. Let's discuss about the temperature effect, right? Say this is also 1 atm, the same pressure is maintained. But let's say now you are with greater temperature. Now you are coming up with some 50 Celsius. So inside you have 50 Celsius, right? Maintain at 50 Celsius. Earlier it was 25 Celsius, right? So 50 Celsius. That means even before the reaction, you have more kinetic energy in the system. Temperature means the kinetic energy, right? Temperature means the kinetic energy. If you are with a greater pressure, temperature than the earlier situation, now your new system is with greater kinetic energy. So to move the piston, less amount of heat will be enough, because more energy is provided by the kinetic energy associated with the temperature. So less heat which is released by the reaction will be enough to move the piston, right, in this kind of situation when the temperature is great, right? So that heat change measured will be changed compared to the 25 Celsius situation. Right now, with a 25 Celsius situation, you are with a less amount of kinetic energy. But here with 50 Celsius situation, you have greater amount of kinetic energy. So greater kinetic energy associated with the temperature means less amount will be enough to move the piston, as more work is done by the temperature, that kinetic energy by the temperature. See? So clearly the heat used to move the piston will change, and that will ultimately change the temperature change we measure from this kind of system. Right? That will ultimately change the enthalpy value, the heat change we measure from this kind of system because of the change in temperature. Right? So temperature will affect the enthalpy. Right? Number three. Right? Amount of matter. Just write like this. Right? Amount of matter. You can write it like amount of matter. Amount of reactants. Products. Involved in the reaction. Simply number of moles. Right? If you are to do the reaction more and more heat will be generated. Right? So it's like this. So the same reaction you can do with the use of 1 mole as well as with the use of 5 moles. This exists. So here you would observe more heat. Heat will release. Here also heat will release. So you would observe more heat from this one. You would observe more heat from this one compared to this. Because this reaction occurs more times compared to this one. 1 mole of times for this reaction, but this is, so 5 moles of times for this reaction, but 1 mole of times for this reaction. This reaction occur more number of times. That means more heat will be generated here. So more will be the temperature increasement with this reaction compared to this. So amount of matter affects. More the amount of matter, more will be the heat generated in a constant pressure process. So more will be the enthalpy. Right? So that is how the amount of matter affect the enthalpy. So we can say the enthalpy is kind of a extensive property. Enthalpy is kind of a extensive property. Depends on the amount of matter. More the matter, more will be the enthalpy. So enthalpy is an extensive property. Just write that thing as well. Enthalpy is an extensive property. Right now? Okay. That is the fourth fact. And fourth one. That was third. And the fourth one is even the physical states associated with the reaction also matter. So physical state. Of reactants and products. So you could have H2O in some reactions in the aqueous form as well as in the gaseous form. So if you have the gaseous form, that means that system is more energized than the H2O in the aqueous form. right? Gaseous form means more energized, no? More thermal energy is associated with the system. That is how that is why the gases are moving at very high speeds, no, gas molecules, right? So gaseous system means more energized system compared to a liquid system, even with the same chemical in the same H2O. So that will affect the amount of that will change the amount of heat, right, need to provide it to push the piston, move the piston up or down, right? So that will ultimately decide the enthalpy change associated with the process, right? So that is the idea. So physical state of reactants and products will also affect the enthalpy change. Clear? Right. These are the 4 factors which affect the enthalpy change, or even the enthalpy. Right? So lamai, as these factors affecting your enthalpy change or enthalpy, right? It is important. It is important to think of some specific values for these parameters, basically to compare two systems. Right? So it's like this. The idea is this, lamai. දැන් ලා මෙහෙම ඉදන්නකෝ. හරිද? දෙයි දන්න ඔයා ළඟ මෙහෙම සිස්ටම්ස් දෙකක් තියෙනවා. right? ඔයා ළඟ ওই විදිහටම සිස්ටම්ස් දෙකක් තියෙනවා. ඔය වැඩි කරන් යනවා ඉතින් හරි. හරි. constant pressure process දෙකක් තමයි කරන් යන්නේ. හරිද? Right? Let's say now you are doing kind of a hydrocarbon combustion. In here, you are doing some hydrocarbon combustion. Right? Here, hydrocarbon combustion. Right? Let's say this is about, let's say, you see, C2H6. And here combustion is done with C3H8. Right? Now you need to compare the two guys. But the thing is, you are maintaining this one at 180 m, and you are maintaining this thing at, let's say, 580, and you are measuring the enthalpy changes. And you are supposed to come up with the best heat generator. So let's say you are doing some research, right, and supposed to come up with the best hydrocarbon to produce more heat. ඉතින් නෝ නියම කරේ. හරි LP gas වල දින තුදෙකම ඒවට ඕනේ මේ දෙකෙන් කවුද heat generation වලට හොඳ එක්කෙනා කියලා තෝරගන්න, හොයාගන්න. අර ඒ වෙලාවේදී ඔය එක්ස්පෙරිමන්ට් එක එක එක්ස්පෙරිමන්ට් එකක් කරන 180 ම අනිත් එක කරන 580 ම වල හරියන්නේ නැහැ ළමයි. ඒතර මේකේ මෙෂර් කරන heat එකෙන් heat change එකෙන් ඔයාලා කිසිම idea එකක් ගන්න බෑනේ about the substance. දැන් මෙතනින් කරන heat change එකෙන් ඔයාලට කිසිම idea එකක් ගන්න බෑනේ about the substance. මෙයන් කවුද හොඳ කියලා idea එකක් ගන්න පුළුවන්ද මේ වගේ experiment එකක් කරලා? ඇයි? Because this TP value will be affected by this one as well. දන්නකො නිකන් නේද? මෙතන value එක වැඩි වුණා, මෙතන value එක අඩු වුණා. එහෙම කියලා දැන් ඔයාට කියන්න බෑ මෙයාට වඩා මෙයා හොඳයි කියලා. Because this effect is not wholly due to the chemical substances, but also due to this one as well. හරි? ඔයාට ඕන මේ chemical substance එකෙන් කවුද හොඳ කියලා බලන්න ඕන. ඔයා මොකද කරන්න ඕනේ? හරි. All the other factors should kept constant. All the other factors which will affect the temperature change should kept constant. All the other factors which affect the enthalpy change should kept constant. For easiness of comparison, which one is best to generate heat? ඉතින් heat engine එක කවුද හොඳ කියලා කම්පෙයාර් කරන්න නම් වාට සිද්ධ වෙනවා මේ දෙන්න ඇරෙන්න enthalpy එකට බලපාන heat change එකට බලපාන අනිත් හැම ෆැක්ටර් එකක්ම constant තියාගන්න. ඉතින් ඔය වගේ ළමයි කම්පෙයාර් කරන්න දෙන්න එක කම්පෙයාර් කරන්න අපිට බෑ right මේ factors වෙනස් වෙද්දී. So that the scientists came up with the idea of standard states. That means each and every experiment will be carried out with some constant values of pressure, amount of reactants, right? And normally taking 298 as the temperature. So some constant values for these things, right, will be taken, right, as standard states. So basically that is for the easiness of comparison and records. They have introduced some special points as standard states. So for pressure, for amount of matter, and even for concentration, the standard states appear, right? That is written there. See, just the bottom of the page number 8, you would observe, you can see it says, as the enthalpy change depends on above factors, it is convenient to use specific values of above functions as the standard states, right? So standard conditions are actually denoted by knots, right? So if you are referring to standard pressure, it will be denoted by P naught, right? If you are referring to standard amount of matter, it is referred to as N naught. One can say theta or naught, right? If you are referring to standard enthalpy, it is going to be H naught. If all the parameters are kept at the standard values, we say such a measured enthalpy is as H naught, standard enthalpy, right? So that is the idea. See, go to the note there at page number 9. It is said, right, standard conditions are denoted by adding the superscript theta to the symbol of the quantity, P naught, H naught, etc. like that, right? So the standard states are written there. As the standard pressure, they are using 1 atm. So the experiment will be done at 1 atm. So that means 1.013 into 10 to the power 5 pascals. So standard amount of matter is referred to as 1 mole. Per 1 mole, always the enthalpies are measured per 1 mole, right? So as the standard concentration for solutions, we take 1 mole solutions, right, as a standard concentration, right? Okay. So these are the standard conditions, right? So standard pressure is given. So temperature, yes, sometimes temperature will be taken as 298. Most of the times it is 298 Kelvin standard temperature, or one can say 25 Celsius. That is, but that is not necessary, right? It's not necessary, right? Normally we take these values, 298 Kelvin or the 25 Celsius as standard temperature, but this is not a must, right? Okay. So note that there is no definite standard temperature. However, 290 Kelvin is used sometimes as specified, right? Okay, a standard amount is 1 mole, standard concentration is 1 mole solutions, right? And standard physical state. So when it comes to standard physical state, right, it is the commonly observed. It is the commonly observed physical state with the substance at these standard states. Normally at 1 atm and 298 Kelvin, the most commonly observed physical state is referred to as the standard physical state, right? Normally, if you are thinking of water, H2O, it is a liquid. That is the common physical state available with the H2O at 1 atm and 25 Celsius. If you are regarding to iodine, it is the I2 solid. Solid is the standard physical state. Chlorine is Cl2 gas. For the Cl2, standard physical state is gas. Oxygen is O2 gas. It's a gas is the standard physical state. So standard physical state is actually the most common physical state at 1 atm and 25 Celsius for a considering substance. Right now? Clear? So those things are given. And for the carbon it's graphite, right? So such things are given at the page number 9, right? So that's clear? Right. That is all about the discussion of enthalpy and the heat and the enthalpy, right? So I think you are clear with the things we have discussed up to now, right? After this, we are supposed to move to the next section. That is actually the exothermic and endothermic reactions. Let's discuss that. Right. So exothermic reactions and endothermic reactions. Next topic. Exothermic and endothermic. Reactions. Exothermic and endothermic reactions. Right. Let's discuss. Right. Okay. What are these exothermic reactions and what are endothermic reactions? First, discuss about the exothermic reactions. Exothermic reactions, right? The idea is this: any reaction happens with liberation of heat. Any reaction occurs with releasing the heat energy is referred to as exothermic reactions. So the acid-base reactions, the basic example, is referred to as an exothermic reaction. So when you are to add an acid to a base, you will feel the increasement of temperature. You will feel that heat if you are to touch the beaker, right? So such reactions, the reactions which release heat energy to outwards when the reaction is happening, are referred to as exothermic reactions, right? Okay. The reactions which release heat energy when producing products. Is referred to as exothermic reactions. Right? Let's come up with this example. This acid-base reaction, which is written in your note. The HCl and NaOH reaction. See, the HCl we know react with NaOH to form what? The NaCl, the salt, water, and some heat as well. Some heat energy will be also produced. Even though we are not written this heat section when writing the normal reactions in the unit 3 as well, right? But here we are mainly concerned about this heat change, right? So with the chemical calculations, basically we concern all about the mass conservation, the mass changes happening with reactions. But here we need to concern about the heat energy as well. This is energetics. All the energy associated with the reaction should be considered. So these are the exothermic reactions. When you producing products by the reaction, heat will also be generated. Right? It's an exothermic reaction. Right. So let's discuss about the energy relationship of this kind of exothermic reaction. Right? So this is your reactant state and this is your product state. Right? So we can consider the enthalpy, the heat energy associated with this thing as heat of reactants or the enthalpy of reactants, and these are the products of the reaction. So we can say the heat energy associated with this that as enthalpy of products. So if you are to concern the energy conservation, right, heat of reactants should be equal to heat of products plus the released heat. So I'll take it as Q. Let's take it as Q. This is the heat released, right? Okay. So heat of the enthalpy of reactants should be equal to enthalpy of products plus the released heat. Right? So we can write like that. So to conserve the energy, initial energy should be equal to the energy after reaction. So enthalpy of reactants should be equal to enthalpy of products plus heat. This says that the enthalpy of reactants will be a higher value than the enthalpy of products. So if it is this is 5, this value should be less than 5, like 2 or like 3 plus 2, like that. So this relationship says that the enthalpy of reactants is going to be a greater value than the enthalpy of products for a exothermic process. So we can write H reactants will be a greater value than the H products. So if you are to think of enthalpy change, which is delta H, which will be equal to H products minus H reactants. For exothermic process, actually the H products will be a smaller value, H reactants will be a larger value. Here. So you are supposed to deduce or deduct. You are supposed to deduct a larger value from a smaller value. You are supposed to deduct a larger value from a smaller value. So this is going to be a negative value. This is going to be a negative value. Right? Like you have to subtract some 3 from 5, right? So 3 minus 5, sorry, 3 minus 5. 3 minus 5 means minus 2. It's a negative value. So for exothermic processes, exothermic reactions, the delta H is going to be negative then. For exothermic processes, delta H is going to be negative then, right? You can say for exothermic processes, the delta H is negative. Delta H is negative, right? Okay, delta H is kind of a negative, right? Now, for exothermic processes, delta H is going to be kind of a negative value, right? Now, okay. So if you are to think of the energy profile for these exothermic reactions, so this is referred to as the enthalpy diagram. The energy profile of this enthalpy gases are referred to as the enthalpy diagram. So at this axis you have the enthalpy, right? Enthalpy, right? Enthalpy or delta H, just H, right? Normally that is given in kilojoules per mole. Or if you are to think of this energy profile or the enthalpy profile, enthalpy diagram, right? Your reactants are with a greater value and your products are with a smaller value. Reactants are with a greater value, products are with a smaller value. So we can mark that thing like this. You're thinking of 2 levels. The higher level is about reactants. The lower level is about products. So reactants are with a greater value, products are with a smaller value for exothermic reactions. So that means if you are to write the reaction arrow here, the reaction arrow is always written from reactants to products. So you would observe clearly the drop in enthalpy. When coming from reactant products, you would observe kind of a drop in enthalpy. So the delta value, the delta H is minus. Delta H is minus. Drop in enthalpy, right? So delta H minus means actually going from reactant to products, the enthalpy drops. Delta H minus means H drops going from reactant products. Delta H minus means delta H minus means H, the H enthalpy drops from reactant products. Enthalpy decreases from reactant products, right now. So some clear idea is there with the sign of the enthalpy change here. For any property, for any parameter, if the delta value is minus, that means that parameter decreases going from reactant products. When the process is happening, going from initial to final, that parameter decreases. That is what the delta value minus means, right? Delta H minus means H decreases when going from reactant products. Clear, right? So this is all you should know about the exothermic processes, right? So for an exothermic process, always the delta H is going to be minus. If the delta H is minus, the process is exothermic. Both are okay. For exothermic process, delta H is minus, and for when considering delta H minus things, those are exothermic, right? Vice versa, those are true, right now. So this is all about exothermic things. You can go to the note as well, right? Let's quickly go to the note, right? I'll discuss about the endothermic stuff as well, right? Quickly go to the note, Lamai, about the exothermic processes, right? All the things I have explained will be there, and things are clear. after that, let's discuss about the endothermic reactions as well. Endothermic reactions. Endothermic reactions. Right. What this means? The opposite of the exothermic, right? When reactants convert into products, right? When reactants convert into products, if the process absorb energy, if the process absorb heat energy from the surrounding to do the process, right? So such processes are referred to as endothermic processes or endothermic reactions, right? When heat is absorbed from the surrounding to do the reaction. To do the reaction means to convert reactants to products. Such reactions are referred to as endothermic, heat absorbing reactions. Right now? Okay. So let's come up with some examples here for endothermic processes. So example. So this is a good example. We are the N2 gas reacting with O2 gas to produce the NO gas. So would have some half values here. So in this lesson, in this enthalpy lessons, you can balance the reactions even with half values. Sorry. Then chemical calculations වගේ වෙන තැන් වලදී අපි කවදාවත් half values වලින් reactions balance කරේ නෑනේ. එහෙම කරන්න බෑ මොකද? E levels වල. But only with the chemical calculation stuff, sorry, only with the energetic stuff, you can balance your reactions with half values. හරි energetics එකේ එහෙම half values වලින් balance කරන්න පුළුවන්. ඒ අරින්න අපිට half values වලින් reactions balance කරන්න බෑ ඒ levels වල, right? You won't get marks there, right? But with energetics it is okay, right? Okay. Then we'll discuss why is that. We'll discuss with the next day's class, right? Why we are able to balance these reactions with half values, right? There is a theory there. We'll discuss with the next class, right? Okay, to do this reaction actually, right? The heat should be absorbed. Without supplying the heat energy, this reaction won't occur. It's very important to have provide some heat to do this process. So it is very clear, right? So if N2 is to react spontaneously without supplying the heat, right, you won't observe 78% of N2 and the 21% of O2. They are at the atmospheric air. Right? N2 O2 නිකම්ම react කරනවා නම් without supplying the heat නේද? ඔයාට කවදාවත් N2 78% O2 21% තියෙන විදිහක් නෑනේ. Those will react eventually. And all the O2 will ends then. හරි ඔක්කොම ටික react කරලා O2 ඉවර වෙලාම යයි එහෙම ගියොත්. So it is very important to supply heat there to react these two guys which are non-reactive at normal conditions, right? So with the supplement of heat you can do so, right? So this reaction occur normally in two systems. The first one is actually when lightning process is happening, lightning with the එක වෙලාවක් තමයි මේ දින react කරන lightning එක ලොකු energy එකක් involve වෙනවනේ. අන්න එතකොට අර true air when the lightning happens, right? The N2 guys and the O2 guys will react with that specific amount of heat energy, right? The other instance where this reaction occur in nature is actually inside the internal combustion engines of your cars and the stuff, right? Think cars වල එහෙම තියෙන internal combustion engine එක ඇතුළෙත් අර spark එක එන වෙලාවේ when you are starting the thing, right? Spark එකත් එක්ක මේ reaction එක වෙනවා, right? N2 will react with the O2. That is the only two situations, normal situations, day-to-day situations we observe this thing, right? This reaction. Otherwise, you have to supply very enormous heat to do this process, right? Okay. So it's a heat absorbing reaction, which is referred to as endothermic process then, right? So let's concern about the kinetics associated with this chemical reaction. So these are the reactants involving with this. So we can consider this the summation of heat energy associated with these two guys as the enthalpy of reactants. And then you have this is the product, the only product here, right? So we can consider it as the enthalpy of products, the heat energy associated with that, right? So you have the heat as well. So to conserve the energy, the heat at the initial thing should be the energy at the initial state should be equal to the energy at the final state, right? So energy at the start of the process is actually the heat of the reactants plus the heat, this thing, right? So this is the heat in, all right? So we can say the Q and this is heat. That will be equal to the heat of the products, right? So we can write it as the relationship heat plus the enthalpy of reactants will be equal to enthalpy of products, right? So this means the enthalpy of products is actually going to be a higher value than the enthalpy of reactants, right? So to fulfill this requirement, it should be like that, no? So if this is 5, this should be like 3 plus 2, right? So basically enthalpy of products should be a greater value than the enthalpy of reactants to fulfill this relationship, which is associated with the endothermic process, right? So we can say the enthalpy of reactants is kind of a smaller value than the enthalpy of products, right? So when it comes to delta H, we know it is all about the final, the products minus the initial, the reactants, no? So the products is coming up with a greater value and the reactants coming up with a smaller value. So greater value minus a smaller value, that is going to be a positive value, like 5 minus 3 is positive 2, no? So delta H is going to be a positive value if the process is endothermic, right? If the process is endothermic, delta H is going to be a positive value. So we can say delta H here is a positive, sorry, greater than 0, positive. For endothermic processes, delta H is going to be a positive value. If the delta H is positive, it is endothermic. If it is endothermic, delta H is positive. Both are true, right? Let's quickly concern about the enthalpy diagram for endothermic process. So in this axis, we can come up with the enthalpy or the H, right? Normally in kilomole, right? So here your products are with a great enthalpy. So products are with a great enthalpy and reactants are with a small enthalpy. Reactants are with a small enthalpy. So if you are to put the reaction arrow here, reaction arrow is always written from reactants products, the arrow of time, initial to final always written, right? So reaction error should be written like this. So this clearly indicates the change in enthalpy is actually a positive value. The smaller value minus, larger value minus the smaller value. Products minus reactants always is going to be a positive value. So with this, again, we can concern about the sign of the delta H. Basically, if the sign of the delta H is positive, that means the enthalpy will increase going from reactant products. If the sign of delta H is positive, delta H positive means H increases when going from reactant products. හරිනේ? delta H positive වෙනවා කියලා කියන ළමයි H කියන එක increase වෙනවා going from reactant products. Increase, positive can increase, negative can decrease. So that is the idea. Delta H positive means H increases going from reactant products. It is clear, no? So this is all about the endothermic processes. So for endothermic processes, delta H is positive, and if the delta H is positive, the process is endothermic. That is true, right now. So that is all about the endothermic processes which are appearing at the page number 10. Right? Okay. The idea is clear. So with this, Lamai, we are actually ending our discussion about the basics of thermodynamics, the basis of energetics. Right? After this section, we will move towards the calculation stuff and the things, the enthalpy terms. Right? The basics, the terminology and the basic stuff we should know to follow the energetics. That is what we have done so far. මෙතනින් පස්සේ අපි කතා කරනවා මුලින්ම enthalpy කියන එක ගැන වැඩිපුර, enthalpy terms and the stuff, right? Afterwards we'll discuss about few more stuff known as entropy and the Gibbs free energy as well, right? So we'll start discussion about specific standard enthalpy terms we have to learn with our A-level syllabus. Such 14 standard enthalpy terms are there to learn, right? Let's discuss one by one. Actually, those are appearing in your page number 11, no? Let's go to those, right? Let's go to the page number 11. පියනවනේ ළමයි. හරි අපිට enthalpy terms 14ක් ඔක්කොම 14 enthalpy terms we have to study under the A-level syllabus. Enthalpy terms 14යි නෙමෙයි දින්නේ, හරි ඊට වඩා දිනවා. අපේ syllabus එකේ තියෙන 14යි. Right? Only 14 they are in our syllabus. Right? Let's go to those. Right? Right. Right. The topic is standard enthalpy changes associated with specific chemical processes or different thermochemical processes. Right? Such 14 are there ළමයි. ඒ 14ත් වැඩිද දින අපිට කරන්න. හරි? බලන්න 14 මෙතන මම මේක අද කතා කරන්නේ නැහැ. අද අපි කතා කරන්නේ first enthalpy term විතරයි. But I'll give you some idea about those things, right? Some general idea about all of these 14 enthalpy terms, right? මේ 14 ගැන පොඩි general idea එකක් අඩු මුලින්ම දෙන්නම්, right? So the first thing we are going to study here is actually standard enthalpy change of reaction. Standard enthalpy change of reaction. මම කිහිපයක් කතා කරනවා තුනක් විතර. ඊට පස්සේ වාඩි තුරු ටික ඔක්කොම තේරුම් ගන්න පුළුවන්. The second thing we are going to discuss is standard enthalpy change of formation. Third one, this is standard enthalpy change of combustion. Right, let's discuss about these symbols. So standard enthalpy change of reaction is symbolized like this: delta H naught R. Standard enthalpy change of formation is symbolized like as delta H naught C. For the combustion, it is delta H, sorry, this is formation, sorry, if no, formation is if, delta H naught for the combustion is C. So we have such, right, 14 to study. Right, let's discuss about this, these symbols. You should have some clear idea about these symbols. Should have some clear idea about these symbols. මේ symbols ගැන හොඳ clear idea එකක් තියෙන්න ඕන ඔයාලට. හරි? බලමු මොකද්ද මේ symbols වලින් කතා කරන්න කියලා. හරි? Right. මේ කතාව. හරි? See how to read this stuff properly. How to read this symbol properly. So this is actually a combination of 1, 2, 3, 4 symbols, right? This whole symbol, total symbol, is a combination of 1, 2, 3, 4 symbols, right? So let's read the stuff properly. Right? This is standard enthalpy change of reaction, right? So this symbol indicates that. So this is we are supposed to read like this: standard, not means standard, huh? Standard enthalpy change of reaction. Standard enthalpy change of reaction. For this one, it is standard enthalpy change of formation. Standard, H is the enthalpy, delta is the change, difference no change of formation. This is regarding formation. So normally the first few ratios will be used, right? So here standard enthalpy change of combustion. Standard enthalpy change of combustion. So lamai here normally with this one, this standard thing, right? They are indicating the pressure is actually 180. With this standard thing, they are indicating the pressure is 180, kept at a standard value. This is the most important thing, right? With the enthalpy, the pressure. This is the heat associated with constant pressure process. So reactants and products are kept at 180 with the standard thing. Most of the time 25 Celsius is there, most of the times. So okay. If solutions are used, 1 mole solutions will be there, right? Solutions are used, 1 mole solutions will be there. And this is regarding 1 mole as well. Amount of thing 1 mole. Standard 11825 standard 1 mole. So the amount of reaction or amount of substance 1 mole, right? So another important thing discussed here. So when it comes to these thermochemical processes, this 1 mole stuff is very important, lamai. We'll discuss with the next topic as well. This 1 mole is very important. Why is that? Because lamai, when we are referring to a chemical reaction, not all the components appearing with stoichiometry 1, no. Not all the components appearing with the stoichiometry 1, no. See, like this. So if you are to think of this reaction, right? right? NaOH reacting with H2SO4 to come up with Na2SO4 and H2O. When you're thinking of this reaction, so where the 1 mole stands, that is very important. So normally this thing reacts with 2 moles to 1 mole ratio. 2 moles to 1 mole ratio. Right? Here also 1 mole appears. Here 2 moles appear. This kind of a change will occur when the reaction occurs for 1 mole of times. When the reaction occurs for 1 mole of times, 2 moles of NaOH reacts with 1 mole of H2SO4 to come up with the 1 mole of Na2SO4 and the 2 moles of H2O, right? So when we are considering the standard situation, we are always between 1 mole, so we have a problem. Where the 1 mole stands? So normally these values are referred to given in kilojoules per mole. So we have problem per mole of which species? Per mole of which species? That is the problem arises. So actually that thing will be indicated here. That thing will be included as the subscript. 1 mole of the chemical which forms the heat associated with 1 mole of the chemical to form. Heat associated with 1 mole of the chemical to combust. Heat associated with 1 mole of reaction to occur. When a reaction is occurring per 1 mole of times, the heat change associated with that, the enthalpy change associated with that. When the reaction occurs for 1 mole of, when the products, when 1 mole of products are to be formed, the enthalpy change happens with that process. When 1 mole of chemical to combust, when 1 mole of specific chemical to combust, the enthalpy change associated with that. So actually that 1 mole stuff standing with the symbol here. That 1 mole is very important, right? For a standard value. Standard amount is 1 mole, right? So we'll discuss about these things one by one. So I think you got a general idea about the symbols used here, right now. Okay, let's start with the first enthalpy change in our syllabus, what we are going to learn. The standard enthalpy change of reaction. Standard enthalpy change of reaction, which will be denoted in literature note R. 1 mole stands at the reaction. When 1 mole of reaction to occur, the standard enthalpy change happens. Standard enthalpy change happens when 1 mole of reaction to occur, right? So when the reaction to occur 1 mole of times, the standard enthalpy change occurs, right? That is the standard enthalpy change of reaction. Let's go to that. So go to the page number 12 and just write. First at this page there, provided there, just write the definition. Definition liya karna bhai. Let's write the definition. Right. After writing definition, you can box this stuff. Really box right? Just write it in red color, count red color and write. Enthalpy change that occurs, enthalpy change that occurs when 1 mole of reaction within brackets 6.022 into 10 to power minus 6.022 into 10 to power 23 6.022 into 10 to power 23 times of change close the brackets happens at standard state, happens at standard states. Right? Enthalpy change that occurs when 1 mole of reaction within brackets 6.022 into the power 23 times of change close brackets happens at standard states. Right? That is the definition. So normally definitions are not going to be asked, right, in A levels. In A levels they won't ask the definitions, but for the next term test, the second term test, they may ask the definitions, but not important when it comes to the A levels. What you should know is just to apply the definition correctly. You should be able to apply the definition correctly, but not to by heart the definition. Right? Okay. So that will be asked. Applying the definition correctly, right, will be examined in your A-level exam. Right? Okay. So let's discuss this thing bit more. Get some clear idea about this thing more. So some reaction, some example reaction is provided in your theory note. With the use of that, we'll have some clear picture of this enthalpy term. So what is the definition here? What is the reaction there given? So they have provided this reaction via the H2 gas reacting with O2 gas to produce H2O. No? So H2 gas reacting with O2 gas to produce the what? H2O gas, no? 2 of H2O gas. So they are saying this thing involves minus 483.7. Delta H naught R minus 483.7 kilojoules mole. 483.7. Right. So let's discuss more about this data. First do this correction there, right? It is minus 483.7 kilojoules mole. Minus 483.7 kilojoules mole, right? So you have to copy this kilojoules, right? Kilojoules mole. Right. So first of all, let's read this stuff clearly. First, let's read this stuff clearly. This data properly. What this says. At this side it says this is all about standard enthalpy change of reaction. This is all about standard enthalpy change of reaction. So that means where the 1 mole stands, yeah, 1 mole stands with the reaction. 1 mole stands with the reaction. So here also they are saying minus 483.7 kilojoules per mole. Kilojoules per mole. Right? Sorry. Right. Kilojoules per mole, right? So minus 483.7 kilojoules per mole. Where this mole stands, right? So this mole means, right, where it stands per mole. That is per mole of reaction, right? That is per mole of reaction here, right? Okay. This says (483.7 kilojoules). 483.7 kilojoules of heat released. This is exothermic. That means heat released. So 483.7 kilojoules of heat released when 1 mole of reaction to occur. When 1 mole of reaction to occur. Got the idea how to read this stuff? 483.7 kilojoules of heat released when 1 mole of reaction to occur at standard state. as enthalpy change of reaction. Right now? Okay, that is how we are supposed to read that thing properly. Got the idea? Right? Let's see. This means right? $483.7 kilojoules of heat or enthalpy, one can say, heat has released. Right, it is minus, right? Negative has released exothermic, right? When 1 mole of reaction to occur. 1 mole of reaction to occur. Or when the reaction occurs for 1 mole of times. Avogadro's amount of time. The idea is clear, no? This is how we are supposed to read this stuff, this data. Right? So actually, where the 1 mole stands? 1 mole stands with what? Actually, 1 mole stands with this. Here the 1 mole. Here the 1 mole, the reaction. When 1 mole of change to occur, when 1 mole of times, the reactants converts to products. That amount of heat change occurred. That amount of heat change occurred. So where the 1 mole stands here, this is the 1 mole situation appearing with this one. This is the 1 mole. So when that happens, right? When that happens, when 1 mole of reaction to occur, 2 moles of H2 will consume. When 1 mole of reaction to occur, 2 moles of H2 will consume. 1 mole of O2 will consume. 2 moles of H2O will consume. Right? That is clear? So when 1 mole of reaction to occur, that is what is referred in the kilojoules per mole term. In 1 mole of times the reaction occurs, 2 moles of H2 will consume. Because when you do this reaction 1 time, 2 H2O molecules will consume. So if you are to do this reaction per 1 mole of times, 2 moles of H2 molecules will consume. 1 mole of O2 will consume and 2 moles of H2O will produce. So that we can say, right, for it was given heat released, right, for 1 mole of reaction to occur, or we can say 83.7 kilojoule given off per 1 mole of reaction. Per 1 mole of reaction. Over time again, per mole again, per mole of reaction, right? So even we can say the same thing can be said like this: given off per 2 moles. See, 2 moles of H2 consumed per 2 moles of H2 gas consumed. Alright, that 1 mole reaction, 2 moles of H2 gas will consume. Same thing. 483.7 kilojoules given off per, in terms of oxygen, it is still the 1 mole. එක සැරයක් reaction එකෙන්ද O2 එක්කෙනෙක් consume වෙනවා. 1 mole of times reaction එක වෙද්දි O2 ලා 1 mole of time consume වෙනවා, right? When 1 mole of O2 gas consumed, or we can say 483.7 kilojoules will be given off when 2 moles of H2O gas to produce. When 2 moles of H2O gas to produce. When reaction occurs for 1 mole of times, 2 moles of H2O gas will produce. 1 to 2 ni reaction අර එකකට මෙයා දෙන්නේ. හරි නේද? ඉතින් ඔය රිලේෂන්ෂිප් එක අපිට ගන්න පුළුවන් ඔය කතාවත් එක්ක. පැහැදිලි? So that is what is written in the page number 12, right? ඔය page number 12 එකේ තමයි ලියලා තියෙන්නේ. See? Right? Is what is written. So just complete this stuff. මේ ටික පුරව ගන්න. මේ ටික හිස්තැන් ටිකක් තියෙනවා නේද? Just complete those. මේ ටික complete කරගන්න. Right නේ? හරි. Right නේ? හරි. අපි යමු අද දවසේ අවසාන වැඩිට. අන්තිම වැඩි. හරි. දැන් අපි යන ළමයි මේ කොහොමද practically මේ වගේ delta H naught R value එකක් measure කරගන්නේ කියලා කතා කරන්නේ. How to come up with or measure or to come up with the delta H naught R value practically. How a reaction procedure will be done and how to use those values obtained by the experiment to calculate delta H naught R. Right? That is what we are going to discuss now. Right? බලමු. කොහොමද experimentally අපි values obtain කරන්නේ? ඊට පස්සේ experiment obtain කර values use කරලා කොහොමද delta H naught R අපි calculate කරන්නේ? Right? That is what we are going to discuss now. Right. දැන් ළමයි මේ සාමාන්‍ය enthalpy change එක denote කරන්නේ මේමනේ. So normally let's come up with the earlier enthalpy term as well, right? So it was like delta H naught R was equal to minus 483.7 kilojoules per mole. ඔහොමනේ තිබ්බේ. හරිද? එතකොට enthalpy term එකක් ගැන කතා කරද්දී right, we need to come up with actually 3 things. We need to find 3 things. Right? If they have asked you to ultimately to calculate the delta H naught R value of a given reaction, so you have to consider on 3 things. තුනක් ගැන කතා කරන්න ඕනේ. මොනවද ඒ ජාත් තුන? එකක් තමයි මෙන්න මෙතන. You have to decide whether the reaction is exothermic or endothermic. In this case it is endothermic, so have to decide the sign. Sign of delta H. Right, sign. You can exothermic endothermic කියලා. Whether it is exo or endo. You have to decide that. If it is exothermic, releasing heat, right, that will be minus. Endo, it will be positive. And you have to calculate this value. මේ value එක calculate කරන්න ඕන. Right? Energy change, heat change, right? Heat change happens in the process. And finally, you need a per mole value. Not just the heat change, we need per mole value. The per mole value. That means you need to come up with the amount of reaction, amount of change. In this case, it's the reaction, amount of reaction. to come up with the per mole value, first you need to know the number of moles reacted. Then you can convert it to per mole. So these three things should be addressed to come up with the total delta H to R value, right? So this thing, deciding the sign of the delta H, actually can be done by looking at the temperature reading of your thermometer. If the temperature increased, from reactant products, that means the reaction process has released the heat. That means it's the exothermic. Delta H negative. If temperature decreased of your thermometer going from reactant products, that means the heat has absorbed by the reaction is endothermic. Delta H, the sign is positive. Right? Are you clear with this thing? No? Not clear? Okay. I'll explain a bit more. Right? It's like this. So, see. So, let's see. Let's discuss about these two situations. Right? So, let's see. You have thermometer here. I'll discuss two things, right? Some situation involved with exothermic process and endothermic process. Right? Okay. So it's like this now. So let's concern these as the reaction sites where the reaction occurs. Right? Okay. So let's say some exothermic process. Exothermic process means reaction sites will give off heat, exothermic. When the reaction occurs at those sites, they will give off heat. That means what happened to the temperature of the solution? As the reaction site is giving off heat, as it's an exothermic process, right? The temperature of the solution will increase. So here, temperature solution will increase. Right? So what about this one? When the reaction sites absorb heat to do the process, to do the reaction, when the sites absorb heat from the solution, which is referred to as an endothermic process, then what will happen? Then the heat of the solution will, the temperature of the solution will decrease as heat is absorbed by the reaction sites. The temperature of the solution will decrease. So that is, so with that, the temperature of the solution will decrease as heat is absorbed to the reaction sites. So heat of the solution is now less, so temperature will drop. So if you observe some temperature increasement with the thermometer, it's an exothermic process. So that the delta H is negative. So delta H is negative. If you see a drop in temperature of your thermometer, that means it's an endothermic process. Your delta H is positive. So that is how the sign will be reduced by merely looking at the temperature change, whether it's increased or decreased. That is clear? Right. Let's discuss about how to measure the heat change. So that is very easy. Measuring the heat change is not that much hard, Lamai. Measuring the heat change. What we are supposed to do to measure the heat change? So I'll write it some other color, right? So not visible that much, no? Right. So heat change. So to measure the heat change, we are coming up with this equation, no? Q is equal to mc delta theta. Q is equal to mc delta theta. That will be used to measure the heat change. So heat change will be measured with the use of Q is equal to mc delta theta. Right? So this is a very important thing, right? So using this equation is very important. So one can say it is the delta Q, no? We are measuring the temperature, heat difference. Right? So when applying this equation, there are few more stuff to concern. We have to concern few more stuff when applying this equation properly. What are those? So this is actually the heat change. This is actually the temperature change. In the solution, just keep that clear. This is temperature change in the solution, right? So when these things happen, the temperature change will occur in the solution, right? And see what this means. This is the specific heat capacity. Specific heat capacity of the solution. Specific heat capacity of the solution, right? So that this should be the mass of the solution, right? So keep that clear, right? So this equation is totally applied to the solution, right? Okay, this is mass of solution. To this, normally we use this m equals dv equation to come up with the mass of the solution. If you know the density of the solution and the volume of the solution, we can use this m equals dv to come up with the mass of the solution. Right? So that combination of these values will give you the heat change of the solution. Heat change of solution. Right? All things will be applied to the solution. So ultimately what we can do is, by measuring the numbers for the solution, we can say that numbers are actually came by the reaction. So heat released by the reaction is equal to heat change of the solution. Heat released by the reaction is equal to heat absorbed by the solution. So that manner we relate that Q value to the heat released by the reaction here. We relate that Q value to the heat absorbed by the reaction here. So actually what we are doing is applying this equation to the solution, and we ultimately equalize that value to the heat change involved with the reaction. Right? That is what we are doing. So that is about the heat change of the process. Right? What about this? Per mole value. So this heat change is given for the whole process, and when regarding enthalpy change, we have to come up with a per mole value, so that the heat calculated like this should be divided by the amount of reaction. Should be divided by the amount of reaction to come up with the per mole value. So this is the heat. With this, we calculate the heat, the total heat involved with the process. And if you need per mole value, we have to divide that total amount of heat involved in the process with the amount of reaction in moles. The kilojoule value should be divided by moles value. Then only kilojoules mole happens. So here we have to come up with the amount of reaction. So that can be should be calculated. That can be basically done by the use of the limit regent. We'll discuss about that thing when solving the question at the next page, right? So we'll go through an example here, right, to have a clear idea about this stuff, right? Okay. Let's go to the page number 13 and see. Oh, you are okay with this stuff? Shape. Let's quickly discuss about a example question, actually, which is appearing at the page number 13. So you can go to the question, Lama. Just read the question first of all, and then I'll solve the same question step by step. What a question එක කියවන්න ළමයි page number වගේ කීයක් තියෙන්නේ? Page number 13 වල තියෙන question ටක් ගාලා කියව ගන්න. Solving part එක මම කතා කරන්න. Right? Right. Let's quickly solve that one. So the situation is like this. So we have a, see what it says. We have a calorimeter, right? And what we are adding to this then? This is referred to as calorimeter, right? Calorimeter means a heat insulated vessel, right? Okay. So calorimeter is there. Right, okay. To this calorimeter, so heat loss won't occur. That is what calorimeter is, right? So to this calorimeter, right, we are adding some thermometer is also there, right? We are adding NaOH and HCl, NaOH AQ and HCl AQ. What are the amounts? 1 mole NaOH, 50 cubic centimeters. And for this one, it is again with 1 mole concentration and 150 cubic centimeters, right? So this is your system, right? So at the end, you will observe this kind of stuff, right? This calorimeter. Right? So you have the solution. Thermometer is also there to measure the stuff, right? So you just add then measure the stuff, right? Okay. So this so reaction sites are there. What they are saying? They are saying the temperature has raised. Temperature has raised. So temperature is increased. The T value is given as 3.4 Celsius. That has increased, right? It's increased value. So temperature increases. Why? Because of releasement of heat from the reaction site, right? Then only temperature of the solution could increase, right? Okay. And the volume here is actually 150 plus 50, 200 centimeter cubes. And what are the other data they have provided? And the solution's density is given as 1 GCM minus 3. And heat capacity is also given as 4200 joules per kilogram per Kelvin. Right. Okay, let's quickly solve this one. First thing. The first thing to do is deciding whether this one is exothermic or endothermic. Deciding the sign of the delta H. Right. First thing is deciding sign of delta H. So here we can say temperature raised, temperature increased, so that it's an exothermic reaction. Show that the delta H naught R is negative, right? So that is how we are supposed to decide the sign of the delta H. It is done. Right, second thing. Amount of heat. Now it is released now. Exothermic now. Heat change, let's say, amount of heat change. So we are supposed to come up with the kilojoules, right? So for this, we can apply the Q equals mc theta. Right, Q equals mc theta can be applied. So to apply the M, first we need to come up with the M, the mass of solution. For the Q equals mc theta, we need the mass of solution. So mass of solution is given by dV. M is equal to dV, no? So density is 1 gcm minus 3. Volume is 200 centimeter cubes. So it is going to be 200 grams. This mass of solution. So with the use of this, we can use the right Q equals mc theta to come up with the heat absorbed. By solution. So heat is released by the reaction sites, and that is absorbed by the solution, right? So heat absorbed by solution can be calculated using Q equals mc theta. So M is 200 grams. Now when applying the M, always apply, when applying the values for this equation, always apply the values in the units of C, in the units of C. So C comes up with the units of kilograms and the Kelvin. No? So apply to this equation the other values, the M and delta theta, in terms of joule and Kelvin. Then only those units will cancel off to ultimately give you the joules value. Right? That is the way of applying the numbers there, right? For the Q equals mc theta. No need of coming up with these units, right? What you need to do is you have to apply the values of the other parameters, which will be tally with the units of the C, right? So here the in terms of kilograms, the C is discussed, so that mass should be applied in kilograms. So it is going to be 200 over 1000 kilograms. The C value is 4200 joules per kilogram per Kelvin, and right, the theta, the change is 3.4. The change in temperature in Kelvin as well as Celsius the same. Celsius change accurate, temperature Kelvin change accurate, ekama change එක lamai, right? So the final value comes up as 2856 kilograms. Sorry, joules, no? So normally delta H values are represented in kilojoules mole. So in kilojoules it is 2.856 kilojoules. This is the heat absorbed by the solution. So if you are to consider no heat loss to occur, we can say the heat given off by reaction is same as the heat absorbed by the solution. Right? Here we consider that no heat loss occurred. Assumption: no heat loss to surrounding. ඒ කියන්නේ කැරණි මීටර් ගන්න නිසා යා හීට් එක ලොස් වෙන්නේ නැහැ. මෙතනින් එළියට යන්නේ නැහැ. හරි. ඔක්කොම යූස් වෙච්ච හීට් එක මෙයාගේ ටෙම්පරේචර් එක අප් කරන්න විතරයි යූස් වෙන්නේ. That is the assumption. Right now? Final thing. The amount of reaction. Amount of reaction. Right. So how to come up with the amount of reaction? Per mole value we need no kilojoules per mole. The kilojoules is okay, sign is okay, kilojoules value is okay. Per mole, amount of reaction is needed. So that will be calculated like this. So we can come up with the limit region first of all, right? And the reaction. This is the reaction NaHAQ reacting with HClAQ, giving you the NaClAQ, and the H2O. Amount of reaction. Let's concern. First copy the number of moles for each species. The NaOH, it is 1 mole 50 cubic centimeters. The value is 0.05 moles. For HCl, it's 1 mole 150 cubic centimeters you added. So value is going to be 0.15. So what is the limit reagent here, Lamai? The reaction occurs 1 to 1. So that means this is your limit reagent, right? So this is your limiting reagent. The thing is actually, Lamai, when the limiting reagent ends, the reaction will stop. When the limiting reagent ends, the reaction will stop. That means at that point, the liberation of heat will stop. The releasement of heat will stop. So until that point only, this heat is released by the reaction. So it is very important to note that, right, not all the HCl has been reacted. When the 0.05 moles of NaOH has been completely reacted and ends, the reaction stopped and releasement of heat stopped there. So that we have to concern that. So always, to come up with the amount of reaction, number of moles of reaction, we have to consider the limit reagent and its stoichiometry with the reaction. Its stoichiometry with the reaction. So this the NaOH is the limit reagent. So we have to consider its stoichiometry with the reaction to come up with the amount of reaction. As NaOH to reaction is 1 to 1, we can say amount of reaction is same as the amount of consumption of NaOH. 1 to 1. So amount of reaction is same as the amount of consumption of NaOH, that is 0.05 moles. So now we can come up with the delta H naught R. Enthalpy change of reaction. So it is going to be the delta H naught R is going to be, it's a minus value, right? It's exothermic, so it's minus. The amount of heat associated is 2.856 kilograms. Sorry, 2.856 not the kilograms, kilojoules. And the amount of reaction, the mole value is actually 0.05. So we have to divide by 0.05 per mole of reaction. Per mole of reaction, we are calculating the value. So this value will be given as 57.1, the minus 57.1. So that is how we are supposed to calculate the delta H naught R. Right now? So quickly complete the stuff. Complete karagan. Right, I think I question has solved. I think you have 2 more questions appearing at the page number 14. Page number 14 the questions they got game. ඒ දෙකත් කරන්න. හරි. එතකොට ඒ වීඩියෝස් දෙකක් අපි දාලා දෙන්නම් ඔයාලට රිවිව් වීඩියෝස් දෙක, right? ඉතින් ඔය දෙක කරන්න. කරලා මේ වීඩියෝස් ටික බලලා ඔයගොල්ලෝගේ හරියද ටික හදා ගන්න, right? This is how you're supposed to do a question regarding the delta H naught R, the range of reaction, right? So that's all for today's work. ඉතින් මේ අද වැඩ ටික මෙතනින් ඉවර වෙනවා, right? So we'll see with the next class. Then thank you and goodbye. See you next week.